All right, so we do have quiz number 7 today, which we will start at 4:20, approximately 4:20. Again, 20 minutes long, unless you have a letter of accommodation. I will start on time, so there will not be any extensions today, anything like we did last time. So please make sure that your computer is working well and all of that. And I had assigned you to look at StatKey over the weekend, but then once I started thinking about it, I realized that probably most of you did not do that. So I'm going to actually play a couple of the recordings, videos from StatKey today, just as an introduction. Don't strain to try to understand everything that's said on the videos, because I'm showing them so that you become maybe 10 or 20% familiar with what StatKey is doing. But much of it you probably won't understand at the moment. Just know that I will be breaking things down a bit more on Wednesday, when we meet on Wednesday. We will be covering chapters 20 and 21, but very not much of those two chapters, because much of those two chapters use the traditional means of doing statistics, and we're going to be using StatKey instead. So it's important that you become familiar with StatKey, but also that you understand some of the basic concepts of what we'll be doing, and also know the difference between what we do and what a student will do in a traditional class, so that and the interpretations also will be very important in this class, so that they have to pay attention to those too. We'll start all of that on Wednesday. Today, again, the videos I will display to you. The first video is an introduction to StatKey, but I will stop it after around 10 minutes or so. The rest of it I'll play when we get back from Thanksgiving. I will play the rest of that because we'll be starting what's called hypothesis testing. And that's it. So let me go ahead and share the screen with you. And let's see if I can find.
Today, chapter 17 and 19, right?
Yes. Today said 17 and 19. Mm-hmm.
Oh, one more question. The last test, is that the final?
There's one more test and then the final.
Okay, so there's one more test and then there's a final, right?
Yeah, the final is required because this is a core course, Rowan core course. The Rowan core courses all have to have finals. So I had no choice on that. Okay, hold on one second. It seems as though I don't have it highlighted, what I'm looking for. Yeah, hopefully everybody knows you received the email regarding the time of the final. I'll review that again, but there's a particular time. I believe for this course it's a Wednesday, and it's for 2 hours. So you have to make sure you're available during that time. I'll review that on Wednesday, I think. Just want to make sure of that. Let's see, here we go. All right, so, and if there's an issue with, it shouldn't be an issue. It shouldn't be an issue. There shouldn't be conflicting times, but if there's some reason there is, I said this in the syllabus, you'll have to take my final early. You can't take it late, all right? So whatever date is given for the final, that is it. So if for some reason you're not going to be able to take the final that day, don't take it. You have to take it early, and you have to notify me early. Please don't have any doctor's appointments or anything else at the time of the final. All right, that's important. All right, so here's StatKey right here. All right, so again, this is the main screen for StatKey. And to get to the videos, if you want to hear them again, you can listen to them obviously on this recording, but you can also just listen to them going directly to StatKey. Just click this button here, and there's something called videos here over here. And so the introduction to StatKey is what I'll be doing first, And again, it's just an introduction. Again, the very first 10 to 11 minutes I'll be showing to you, and then I'll stop that and then begin the second one, which is called Bootstrap Confidence Intervals. So those are the two things we'll listen to today before we have our quiz.
Hi, this is Robin Locke, and this video will give a brief introduction to StatKey, which is a set of browser-based dynamic statistics tools that have been developed for teaching simulation-based methods to introductory statistics students. They are freely available from lock5stat.com and can also be downloaded as a Google Chrome app. The developers are the Lock5 author team, who've recently produced a book called Statistics Unlocking the Power of Data. Here's the team here. And this has just come out now from Wiley as a new book which uses randomization and bootstrap techniques as the foundations for developing inference with students. Program support comes from Rich Sharp at Stanford University, who did a lot of the initial programming, and then Ed Harcourt and Kevin Angstadt, who are at St. Lawrence University, have done a lot of the follow-up work, and it's all programmed in JavaScript. So here's what you'll see as the main StatKey page. Everything runs off of the single page here. And so let me just give you a quick orientation to what's here, and then we'll delve into some of the individual parts. The descriptive statistics and graphics section is standard procedures for displaying results for single categorical or quantitative variables, as well as relationships between pairs of variables, both graphically and with summary statistics. Sampling distributions we've implemented for sampling from a population with getting a mean or a proportion. The heart of the program really comes in the sections on bootstrap confidence intervals for doing bootstrap distributions for single quantitative variables, single categorical variables, differences in means, difference in proportions, and also quantitative relationships. And for all those things, we have a similar set of randomization tests set up in this section over here. We have some replacements for the standard back of the book paper tables to do calculations for normal, t, chi-squared, and f distributions. We've implemented a few slightly more advanced procedures, all by randomization tests for doing chi-square goodness of fit tests for single categorical variables, associations between two categorical variables, one-way ANOVA, and ANOVA for regression. And there's a help button down here which will give you some videos and other support for helping you use StatKey. So that's the basic setup for the whole program. And so let's get in and look and see what it actually does. So we'll switch over to a live StatKey screen here. And let's start with a sampling distribution, something that may be fairly familiar. And let's do a sampling distribution for a mean. We'll pick this option here. Most of the StatKey procedures will start with a little menu item up in the top here, which has a variety of data sets that are pre-built in the StatKey you can choose from. Most of these are tied into the textbook. So let's choose the Stat Grad Schools. This has got some data on the number of statistics students at graduate programs around the country, thinking this is a population. Here's what the actual data looks like. So we've got, I think, 82 statistics programs, and there's all of their enrollment. So we're thinking this is the population. Over here we see a distribution of that population with a mean enrollment of, looks like just over 53, median and standard deviation given there. Okay, and then from this, anything in blue we can sort of edit or use as a button. So we'll start off with a default sample size of 10. Come over here and generate one sample. And pretty consistently, a StatKey down here will be our sample window. And so here's a sample size 10. We can see here's the 10 schools that actually got chosen for this particular sample. This is sampling without replacement. Okay, and the mean for this particular sample is 39.3, which shows up here. Okay, if we generate a second sample, this plot changes and we get the new mean displayed in here. We can quickly go to generate 10 samples at a time, 100 samples at a time, or 1,000 samples at a time. And it all goes pretty quickly. So now we've got a pretty good idea what the sampling distribution looks like for samples of size 10 from this population. And one of the nice features here is as we move the cursor around through the distribution here, each of these sample means that's plotted in the dot plot here relates back to a particular sample that we can see over here. So the StatKey remembers exactly which sample each of the now 1,112 sample means come from. Okay, and so we get a good idea of the picture of the sample means as it shows up there. Now if we want to change the sample size, click on this and say we'd rather have samples size 15. So to generate 1,000 samples of size 15 from this population, We'll click this button here, and we see now the sampling distribution for samples of size 15, and we can compare those, especially comparing things to the standard deviation, to what we saw when we had samples of size 10. So now let's go over and back to the main StatKey page, which we can always get to by going to the icon up here and get back to the main page. So let's move over here to sampling distribution for proportion. And although we do have some examples built in, let's put our own proportion in. So let's suppose we want to sample from a population where the proportion is 0.3. Put that in here. And let's change the sample size to 100. Choose that here. And so now we generate our one sample. This one got 33 out of 100, so sample proportion of 0.33, which is plotted down here. We can quickly generate 1,000 of these. So now we get a sampling distribution of the proportions, which is centered around 0.3 as we expect. A standard deviation or standard error of the proportions of about 0.045. And again, each of these dots corresponds to a sample count we see over here. What I'm going to do now is reset this plot. So we'll start over again and change over here to the confidence interval option as a display. Here's our population of 0.3 in the middle. And so let's generate our one sample. Here's the sample proportion of 0.32. And the green bars here represent a confidence interval around that proportion of 0.32, which we notice does successfully capture the proportion of 0.3. Here's a second sample, third. So now each of our samples is going to be represented by a confidence interval. And so here's 10 confidence intervals. Who knows one sample proportion of 0.39 did miss the proportion of 0.3 in its interval. So we've got one that's missed so far out of 10. Here's 20. 30, 40, here's 50. We've got another one that's missed here. So this one's missed on the low side at 0.21. Let's generate a few more. Here's a couple more that have missed. And so out of 100, we've got a total of 92 intervals which successfully captured the proportion of 0.3 and 8 that have missed. And we can see the ones that miss are on the low side here at 0.18. 0.21, 0.20, that corresponds to these values at the low end of the sampling distribution. And the ones that miss on the high end, 0.39, 0.42, 0.46, correspond to these values out here. So those are the ones that miss on either side. So we can get some idea of what the sampling distribution looks like, but also the fact that in the sampling distributions, we see some proportions on the high end and low end, which lead to an interval which misses the true proportion, as we see that. And we could change this if we want to see 90% intervals, okay, which are not quite as successful as we go along there. All right, let's go back to the main StatKey menu now. So one of the difficulties for using sampling distributions in practice is that we really can't generate hundreds and thousands of samples from the same population to see what the distribution looks like. So that's where the idea of a bootstrap confidence interval comes in. So let's look at a bootstrap for a single mean. Okay, and again, we've got several examples built in here. Let's choose Mustang prices. So here's a sample that a student took of prices for used Mustangs, the cars on the web. Has a mean of 15.98, so about 16,000. These are thousands of dollars. About $16,000 is the mean price of the Mustangs. Here's the distribution of the 25 Mustangs in the sample. Now when we generate one sample, as a bootstrap sample, it's going to sample from the original sample with replacement another 25 cars. So notice, for example, this $45,000 car didn't get selected in the sample, needed a $37,000 car. And some of these down here got selected more often. And so the mean for this particular sample is only 13.36. If we generate another sample, we get a new sample down here and a different mean, in this case 16.26. Again, we can do that 10 at a time, 100 at a time, or 1,000 at a time to now get a good idea of what the bootstrap distribution would be for sample means using samples with replacement from the original sample of 25 cars. Okay, and especially we can look here at the standard deviation here, which becomes a good estimate of the standard error of samples of size 25 from this particular population. But also, if we want to get a confidence interval, now we're going to use the two-tailed option here. And if we click that, by default, we get 95% in the middle, and we chop 2.5% off of each tail. And so we see a 95% confidence interval here will go from about 11.83 to 20.18. And anything that's in blue is editable. So if we click on the 0.95 and say, I'd really rather see where the middle 90% is, I get a slightly narrower interval, chopping 5% off of each tail. Or change that to 0.99. And I get a wide interval that takes only 5 values or 6 values off of each tail to get our interval. Okay, so that would be how we would get confidence interval from a bootstrap distribution for a mean. If we'd rather change this to a different parameter like the standard deviation, we could do that and get a distribution of the standard deviation instead, and now we find a confidence interval for standard deviation. Okay, so let's go back to the main menu. Okay, we can do that by sampling for single means, medians or standard deviations, single proportions, difference in means, difference in proportions, or a slope or a confidence interval. In each case, the intervals would, the sampling distribution would be generated by sampling with the replacement from the original sample and calculate a statistic for each sample. Okay, so now we'll move over to the randomization test.
Okay, so that's all we'll listen to for that first video. And now we'll start the second video, which is going to focus on the what are called bootstrap confidence intervals. That's what we're going to be working on starting next class. Okay, so let's go ahead and choose that again. Oh.
Hi, I'm Patty Fraser-Locke, and this is a brief introduction to bootstrap confidence intervals. Bootstrap confidence intervals are a way to create confidence intervals using only the data in your sample and some very basic ideas from descriptive statistics. So bootstrapping, key phrase, let your data be your guide. This method was developed by Brad Efron at Stanford University. It comes from the phrase pulling oneself up by one's bootstraps, which refers to reaching down, grabbing the straps on your boots and lifting yourself right off the ground, which seems impossible. It is impossible. And this method seems quite amazing also, I think, the first time you see it. So bootstrapping works because we assume the population is many copies of the original sample. So let's look at an example. Suppose we have a random sample of 6 people. Here are our 6 people, and we're measuring some statistic with these people. Measure maybe the average IQ or the proportion who voted in the last election or correlation between height and weight or some sample statistic we're computing from this sample of 6 people. For bootstrapping, we take our original sample and we assume that the population is many copies. So this gives us a simulated population to sample from. So here is our original sample of 6 people. Notice that the simulated population is just these same 6 people repeated over and over and over again, infinitely often. So what does this mean in practice? We sample with replacement from the original sample, since each of these people represents many others in the possible population, using the same sample size because we're estimating variability here and sample size is key. So we're taking a sample of size 6 with replacement from this original sample. So let's do that. We sample one person and we get this blonde person, and we sample again, we get the red-headed person. We sample again, we get the blonde person again. Remember, that's possible because we're sampling with replacement and because this person represents many people in the population who have the same characteristic. We sample again, we get this person, or this round person, get the round person again, and finally get this rather scary-looking person. So this is one bootstrap sample, starting with our original sample. So again, we assume the population is many copies of the original sample. The key idea to see how a statistic behaves, in particular to measure the variability in the statistic, we take many samples with replacement from the original sample using the same sample size. So let's look at an example. What is the average price of a used Mustang car? So one of our students did this, selected a random sample of 25 used Mustang cars from autotrader.com and recorded the price in thousands for each car. So here's a pictorial representation of our sample of 25 used Mustang cars, and there's a dot plot of the cars, and there's the sample size, mean, and standard deviation. Again, this is all your students need to know in order to be able to start constructing and understanding confidence intervals. So our best estimate for the average price of used Mustangs is $15,980 from this sample mean, which is in thousands of dollars. And the question is, how accurate is that estimate? We want some kind of confidence interval or margin of error to put with that best estimate. Key question, how much can we expect the sample means to vary just by random chance? So here's our original sample again. We take a bootstrap sample, which means sampling with replacement with a sample size of 25 from that original sample. And so here's our bootstrap sample. Notice that this blue Mustang car got selected 3 times over here. This gold Mustang convertible did not get selected at all in our bootstrap sample. Same idea, same pictorial as we had before with the 6 stick figures. So here's the idea. We have our original sample, and from that we compute some sample statistic that we're interested in. From the original sample, we construct many, many, many bootstrap samples, doing this over and over again. We compute the bootstrap statistic, same statistic as the sample statistic, over and over again, and we gather all of those into what we call the bootstrap distribution. And because we want to do this thousands of times, we need technology. And so we have developed a set of tools that enable this to be done quite easily. They're freely available to everyone at lock5stat.com. There's another one of these introductory videos that explicitly talks about using StatKey if you want to take a look at that. So let's go to StatKey now, and here is the main menu. Here are bootstrap confidence intervals here, and you get there by going to lock5stat.com. And we're interested at the moment in a confidence interval for a single mean. Notice, however, StatKey has descriptive statistics, confidence intervals, hypothesis tests, sampling distributions, theoretical distributions, and more advanced randomization tests. At the moment, we're doing a bootstrap confidence interval for a mean. Let's go there. There are many built-in data sets connected with our book, Statistics Unlocking the Power of Data. One of them is this Mustang price data set. So let's go there. And you see right here, this area will always have the original sample. And notice that here's the dot plot we saw earlier, although now we can hover over the points and see that this very expensive Mustang car was $45,000. Here's one for $37,900. Some very cheap ones also down here. Here's the sample size, the mean, median, standard deviation, all that we saw earlier. Okay, we're going to generate one bootstrap sample. Here it is down here. Notice that this expensive $45,000 car did not get picked. 2 of these 3 got picked. These 4, 3 of them got picked twice. So this is a bootstrap sample, just as we talked about it earlier. Sampling with replacement from this data set with sample size 25. We've computed the mean. It's 14.328, and that 14.328 is plotted over here on this area, which will become the bootstrap distribution. So again, this is the original sample. This is the most recent bootstrap sample, the only one so far now. And this is the bootstrap distribution. We generate another sample, and again, we didn't get the expensive one. We got both of these, but not the 2 more expensive than that. These ones we got picked many, many times, all at 7 here. So there's 2 7s here and a whole lot here. Again, another bootstrap sample. This mean is 14.484, and now both means are plotted here. We can generate another sample. We get this one, 16.38. We see that plotted here. We can generate another one. 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 You can hover over any of these and see the bootstrap sample that gave rise to that bootstrap statistic, that bootstrap mean. Okay, let's generate 1,000. So there is a bootstrap distribution. We can generate another 1,000 if we want. It doesn't take very long. And again, still hovering over these will show you the bootstrap statistics. So if you watch over here and try not to get seasick, you can see that every one of these gives us one. We can see why these are quite a bit out in the upper tail, and we can see that that's because those bootstrap samples happen to over-sample these expensive cars. Down here at the other end, these small ones are so small because they didn't end up getting these. So you get to talk a lot about randomness and variability in the sample means. These values here, it tells me that I happen to have done 2008 bootstrap samples at this point. Here's the mean of that distribution, and here's the standard deviation of that distribution. And that standard deviation is really 2.134 in this case. It's just the standard deviation of all these 2,000 plus bootstrap statistics. If we go back to the slideshow, here's a previous simulation that we did, and that value, that standard deviation of these bootstrap statistics, is an estimate of the same of the standard error, the same standard error that we can find by formulas also. And so how are we going to So there's two ways to find a bootstrap distribution, to use a bootstrap distribution to get a confidence interval. The first way is to use that standard error. So the standard deviation of the bootstrap statistics estimates the standard error of the sample statistic, and a quick interval estimate is to use the original statistic plus or minus 2 times the standard error. So for the mean Mustang price, this original sample mean was 15.98 in thousands of dollars, plus or minus 2 times the standard error that we found from the bootstrap distribution. And we compute that to be 11.624 up to 20.336. There's a second method to use the bootstrap distribution to get a confidence interval. And so let's go back over to StatKey to find that. And actually, let me click one more time here. Instead of using the standard error to estimate the middle 95% from the empirical rule, we can find the middle 95% directly, since we have all of those sample means, bootstrap sample means stored. So now we'll go back over to StatKey. There's a two-tail button here, and if you click on this, 95% is the default, and it keeps 95% in the center here and cuts off 2.5% from each tail, giving a 95% confidence interval of $11.856 thousand to $20.153 thousand. Very similar to what we found using the other method. We find that both these methods are really valuable. This method is a wonderful visual display that helps students really think about 95% intervals, and the other method kind of sets them up for later on in the course. In Chapter 6, we go back and do the shortcut, what we call the shortcut formulas, and they're all set up to take the sample statistic and add plus or minus something that has to do with the standard error. And so they both really lead them to a deeper understanding of a confidence interval and to what is to come later. Again, the only thing they need in order to get to this point to really understand confidence intervals is being able to read a dot plot and knowing about sample statistics, means, proportions, difference in means, those things. Okay, let's go back to PowerPoint and look one more time at this Mustang prices. And so again, we keep the 95% in the middle, chop 2.5% off of each tail, and always interpret in context. For this simulation, we're 95% sure that the mean price for Mustangs is between $11,930 right there and $20,238 right there. So we keep the 95% of statistics and look at these values to give us the 95% confidence interval. And One more thing before we leave, there's the standard deviation from the simulation, 2.178. You'll get slightly different answers with different simulations. That again is the standard error. And here we show the shortcut formula. This is a sample mean, so the standard error is S over the square root of n. And it's very, very close to what we get with the simulated bootstrap standard error. Okay, let's do a second example. This one is for a proportion. And so this is a poll of likely voters in October 2012, just before the presidential election of 2012. The poll asked 722 likely voters in Ohio who they planned to vote for, and 368 choose Obama, 339 choose Romney, 15 choose otherwise. And we want to find a 95% confidence interval for the proportion of Obama supporters in Ohio. So remember those numbers in our sample. 368 choose Obama out of 722. If we go back to StatKey, now we want to go back to the main menu. Now we're doing a confidence interval for a proportion. And there's an edit data key. You can edit data. You can enter your own data in any of the options. It's easiest to enter for a proportion because we just need to know that it was 368 out of 722 likely voters. And there's our original sample again. We can generate a bootstrap statistic. It works exactly the same way, same sample size. Now we are sampling with replacement from voters who are picking either Obama or not Obama. And for this particular bootstrap sample, we got 355 out of 722 or 0.492, and it's plotted here. We can generate some more. We can generate 1,000, and we can find either use this standard error there or use the 95%. And we get 0.472 to 0.546 as the proportion, as a 95% confidence interval for the proportion who plans to vote for Obama in October of 2012. Okay. Using StatKey, so here's another simulation, 0.018, almost exactly the same as we had on the previous simulation, and 95% here. We could also use this standard error using the other method. The original statistic is 0.51, plus or minus 2 times the standard error, and we get 0.474 to 0.546, almost exactly the same as we get using the exact 95% of samples in the middle method. Okay, let's do a third example, Diet Cola and calcium. So the question here is, what is the difference in mean amount of calcium excreted between people who drink Diet Cola and people who drink water? So in this experiment, they had 8 people in each group. One of the groups of 8 drank Diet Cola, the other group drank water, and then they collected their urine for 3 days afterwards and measured the amount of calcium in the urine. And the instructions are to find a 90% confidence interval for the difference in means. So we go back over to StatKey and back to the main menu. Now we want to do a confidence interval for a difference in means. And so we get to here. The calcium in Diet Cola is one of the included data sets. So here is the dot plot. Here are the amount of calcium excreted for the water drinkers. Here's the amount of calcium excreted for the Diet Cola drinkers. There's some overlap, although it looks like the Diet Cola drinkers leach more calcium, and that's the question, whether Diet Cola does leach calcium out of the system. So we generate one sample, same method always, which makes it really quite easy for the students to digest. Here we're taking a sample of size 8 with replacement from the water drinkers to get this bootstrap group, sampling with replacement from the Diet Cola drinkers with a sample of size 8 to get this bootstrap group. The means here are 56.875 and 49.25. The difference in means, which is the statistic we care about for this bootstrap sample, is 7.63. And we can generate another. Again, we're building up our bootstrap distribution on the left there. Generate 1,000. And if we do a two-tail, the default is always a 95% confidence interval. But to find a 90% confidence interval, we click on this box here, put in the fact that we want 90% instead of 95%, and there's our answer. We are 90% confident that the difference in amount of calcium excreted between Diet Cola drinkers and water drinkers is 3.375 to 10. Okay. So, why does the bootstrap work? So here is a sampling distribution. We have some population. There is some mean for this population. It's fixed. We don't know what it is. We sample from the population, and there's one of our sample statistics. Notice that it's not the same as mu, but it's not that far off. Take another sample. It's not the same as the first sample, so the students get this idea of sampling variability, and it's not the same as mu, but they're close. Take another one and take a whole lot of them, and we're creating a sampling distribution here so that students see the familiar shape of the normal curve. They're clustered around, centered at mu, and they have a certain variability depending on variability of the original population and sample size. So this is great. We want students to have this image in their head, but in practice, we don't see the tree. We don't know the entire population. We don't see all the seeds. We only have one seed. So there's our one seed. If we're estimating a mean here, that's our sample mean. What can we do with just one seed? And maybe you all repeat in tune with me. We grow a new tree. And that's what bootstrapping is all about. We create the simulated bootstrap population from the sample that we have, and we sample from that simulated bootstrap population. And the amazing thing is we get a sampling distribution that's very similar to the sampling distribution from the entire population. And so there's our sampling distribution. And we estimate the distribution and variability, or the standard error, of the sample means from these bootstrap statistics. There's our mu from the original. And so the golden rule of bootstraps here is that the bootstrap statistics are to the original statistic as the original statistic is to the population parameter. That makes the whole thing go. Thanks for listening, and if you want additional information on bootstrap statistics, you can find it at www.log5stat.com. Thanks very much.
Okay, so there was a lot there to digest. I don't expect you to have understood most of that, maybe 10 or 20%. I was hoping that you would probably understand at this point. We're going to go into what a confidence interval is in more detail on Wednesday. We're going to be using chapters 20 and 21 in the textbook, but only the beginning sections. We're not going to go into all of the sections in those two chapters because we're not going to be using the traditional formulas to create what are called confidence intervals. We're going to be using the stat key just as she has shown in the video. And it's very easy to use once you use it. The difficulty is not in creating them. The difficulty is in interpreting them. At first, you'll have to get used to the idea of interpreting what a confidence interval is. It's a little bit different than what you're used to. And but that's the main goal of doing this in this course is interpretation. So I'm not going to be asking you on a test or a quiz to create one of these, but you need to practice using them so that you get a feeling for how they're used. Because one of the things I will test you on is interpretation and things like, well, if you increase that 95, if you increase that 90% that she talked about, you increase it to 95%, what happens to the length of the interval, that sort of thing. That's where by playing around with it, you get an idea of those types of things. So as I had mentioned, I think last time, it's very important to actually get used to using this, the stack key. And so I will give you some exercises, some sample questions to do, so that you get used to using it. But don't think that because I'm not grading it, it's a waste of your time to do these exercises. Again, the next test will be involve, you know, I will have to figure out how to get these pictures of these bootstrap distributions into Canvas, into a test, but I'll figure it out. But the most important thing is that you learn how to do the interpretation part, which of course I will teach you that. But
So, Pastor, I have a question real quick. When is the next test?
Well, let's see. Let me take a look at this. I have the syllabus open here, so I won't display it to you, but let me just take a quick look when it's supposed to be. It's supposed to be on the last day of class, which is December the 9th, Wednesday, December 9th. And then I believe, if I'm not mistaken, Thursday is supposed to be the reading day that you guys have. But since this is everything is online here, you'll be doing everything on your own. I believe the following week is our final exam. Comprehensive final exam will be for your class. If I remember correctly, it's on a Wednesday, and there's 2 hours allotted to it. So you should have received an email about it 2 or 3 weeks ago, I believe. An email that you should have received. I'll review the dates of the final exam next time. It is required that you take the final. It's required that you take test 3. As far as quizzes are concerned, there will be a quiz next Monday. So it'll be about what's in the textbook, and also these bootstrap confidence intervals. And then there will be quiz, and that's quiz 8, because we'll be taking quiz 9 today. Excuse me, quiz 7 today. And then quiz 9, now obviously next week is the week of Thanksgiving. So there will be a class on Monday where we will have quiz 8. And then there will be a on Wednesday of next week. There will be no virtual class, but I will pre-record an introduction to what's called hypothesis testing. So, and obviously how to use StatKey a little bit too. And then when you get back to class on the 30th, we have 2 more class sessions using the StatKey with hypothesis tests. They call them randomization tests in StatKey. And then on Monday, the December 7th is when we have our quiz number 9, the last quiz, and we'll have a review for test number 3, similar to what we did last time. And then we have test 3 on December 9th, and then the following week we have our final.
Will test 3 will be all math, just like the last test?
All what? Math, did you say?
Yeah, math.
No, I believe there was. No, there'll be some math and some interpretations. I think there was a mix of those last time too. Wasn't all math, I don't think. But yeah, there will be, obviously we'll be covering, starting with chapters 14, right? Chapter 14, I believe, it's when we started this last section. So starting with chapter 14, straight through all of the StatKey stuff will be what we'll cover in test number 3. And it'll be a mix of things, multiple choice, just like the other 2. All right. Any other questions? Now, one thing I wanted to bring to your attention for the next 2 minutes, we have, or 3 minutes. Let's go back to this. Is a phrase that phrases that they used in the videos. One phrase they used was sampling without replacement, and then they talked about sampling with replacement. Now, what do we mean by those 2 terms? Well, picture having a bag full of tennis balls. Let's say there's 3 types of tennis ball, 3 colored types, 3 colors of tennis balls inside the bag. Maybe we have white tennis balls and we have yellow tennis balls, green tennis balls. I believe tennis balls come in those colors. Suppose there's 30 yellow tennis balls in the bag out of 100 tennis balls. If we're sampling without replacement, let's say we pick a ball out and we find that it's yellow. When we sample without replacement, once we're done with that first ball, we don't put it back into the bag. All right. When we're ready to select the second ball, we leave it out of the bag. So that's called sampling without replacement. Now, what happens is that the probability changes for selecting a yellow ball. On that first yellow ball, there was 30 in the bag, 30 yellow balls in the bag, a total of 100 balls. That means there's a 30% chance of selecting the yellow ball in the first try. Once we've selected that yellow ball and we don't put it back in, then the probability of selecting a yellow ball on the second try changes. Because since we didn't put the ball back, we now have 99 balls left and we have 29 yellow balls left. So the probability of selecting a yellow ball in the second try has changed. It's now 29 divided by 99. Now, if we're sampling with replacement, that means after we've selected that first ball, we put it back into the bag. All right. And that means the probability of selecting the second ball that's yellow has not changed. That's called sampling with replacement. And they mentioned in the videos that normally when we do samples or surveys, we sample without replacement. But in the case of where we're doing the bootstrap samples, we sample with replacement, and that's why it works. We'll get into that more next time. So anyway, it's 4:20. Your quiz should be now available to you at 4:20. And again, you have 20 minutes to complete it. For those of you who have, if anybody does have any letters of accommodation, you would have a different time, but most of you have 20 minutes. So you may begin. And I'll shut off the recording now.